All right, welcome. Today, we're cracking open the architect's handbook to get a look at the invisible nervous system that powers pretty much all modern software. We're talking about inter-process communication, or IPC. If you've ever wondered how hundreds of separate tiny services can work together to act like one massive, powerful application, well, this is the secret language that makes it all happen. And this idea of a nervous system is absolutely perfect. Think about it. Without communication, all you have is a bunch of isolated parts just sitting there. IPC is what lets them coordinate, react, and actually work together as a single organism that can solve really complex problems. So here's how we're going to break it all down. First, we'll cover why services need to talk in the first place. Then we'll build our shared dictionary of terms. From there, we'll get into the rules of interaction, the dimension of time, look at the tools you'll use, and then we'll wrap it all up with 5 key takeaways you can use right away. All right, let's dive right in. First up, why do services even need to talk to each other? Well, it really comes down to a huge shift in how we think about and design software today, a shift that makes communication an absolute must-have. And this slide just nails the evolution, right? We used to build these monolithic giants, one huge, powerful piece of code. But they were fragile. If one little part failed, the whole system could grind to a halt. Now we build with microservices. Think of them as small, elite, specialized teams. Each one is a master of its craft. But for them to succeed, they need constant radio chatter, and that's our IPC, to coordinate their mission. Okay, next up, the dictionary. And I gotta say, this section is absolutely crucial. Because if your teams don't share a precise vocabulary for how services communicate, they literally can't build systems that work together reliably. So let's get on the same page and establish that shared language right now. And this is exactly why this matters so much. You see, when one team says they're publishing an event, and another team talks about making a request, are they actually talking about the same thing? Maybe. But that ambiguity leads to what we call architectural mismatches. These are the silent killers of complex projects. Getting the language right, being precise, is our first line of defense. It stops those weird, hard-to-find bugs that only pop up when different services, built by different teams, try to talk to each other. So let's build our dictionary from the ground up, starting with the most basic term, data. This is as raw as it gets. Just ones and zeros on a wire, unprocessed signals. By itself, data has no real meaning. Imagine a smart thermostat sending a raw stream of voltage readings. That stream of numbers, that's just data. Now, when we take that raw data and we add some context, it gets a promotion. It becomes information. So the number 42 becomes customer ID 42. That raw voltage stream from our thermostat gets processed and becomes current temperature, 72 degrees. See, now we have meaningful facts the system can actually do something with. So what's a message? Well, a message is simply information that's on the move. It's not sitting in a database or a file yet. It's being held temporarily in a buffer, maybe in a network queue, while it's in transit, going from a sender to a receiver. Our current temperature, 72 degrees, is now packaged up, sitting in memory, and just waiting to be sent across the network. And finally, we get to content, which you'll often hear called the payload. This is the whole shebang. It's the complete package. It has the business information we just talked about, the 72 degrees, but it's wrapped in all the networking metadata it needs for delivery, things like headers, routing info, the instructions. So our temperature information is now inside a bigger package that says, hey, send this to the central heating service and has a timestamp. This distinction is so important. The payload is the business value plus the delivery instructions. Okay, this table here is basically the Rosetta Stone for software architects. Different tools and technologies use different words for the exact same concepts, and this is where those mismatches we talked about really happen. For instance, a team using a message queue like Kafka will talk about a producer that publishes a message, but a team building a web API, they'll talk about a caller making a request. This table harmonizes all that language. It shows you that underneath it all, we're always just dealing with senders and receivers. Knowing these synonyms means you can jump between tech stacks and still understand the core pattern that's at play. Okay, so with our dictionary all set, we can now move on to the actual rules of interaction. And it turns out, pretty much every single conversation that happens between software components can be neatly categorized just by answering 2 really simple questions. And here they are. These two simple questions define everything. First, who's this message for? Is it a one-to-one, direct message, a one-to-many memo, or a broadcast to absolutely everyone? And second, does the sender need to get an immediate reply before it can continue with its own work? The answers to these two questions will tell us exactly which communication pattern to use. So let's zoom in on one of the most important patterns, which we get when we answer no to that second question. It's called fire and forget. And the check engine light in your car is the perfect analogy here. The car's computer senses a problem, it flips on the light to let you know, and then it just goes right back to running the engine. It sends the signal and moves on. It doesn't slam on the brakes and wait for you to say, okay, got it, I see the light. And this brings us to a really critical architectural trade-off. Fire and forget is all about prioritizing scalability. By not waiting around for a reply, a service can process things incredibly fast, achieving huge throughput. This is perfect for something like logging, where if you lose one single log message, it's probably not the end of the world. But on the other side, you have request reply, which prioritizes fault tolerance. You give up a little speed in exchange for a guarantee that the message was received and the work was done. This is non-negotiable for something like a financial transaction. I mean, can you imagine if your bank used fire and forget for your money transfer? You'd hit send and just hope for the best? No way. This leads us perfectly into our next big concept. And honestly, this one's a total game changer, the dimension of time. Really understanding the difference between synchronous and asynchronous communication is absolutely fundamental if you want to design truly resilient systems. So this brings us to one of the most fundamental questions you can ask as an architect. It's a question that will dictate pretty much everything about how resilient and fault-tolerant your system can be. And the question is this: do the sender and the receiver have to be online, connected, and available at the exact same instant for their conversation to actually succeed? The best way to explain the difference is with a simple analogy. Synchronous communication? That's a live phone call. Both of you have to be on the line at the exact same time. If the other person doesn't pick up, the call fails. End of story. But asynchronous communication is like postal mail. The sender can drop a letter in the mailbox, that's our intermediary, and just walk away. The receiver can then pick it up whenever they're ready. They are completely decoupled in time. And this freedom, this ability to not be locked into the same moment in time, has a name: temporal decoupling. And look, this isn't just some fancy term. It is the architectural superpower that lets our systems survive failures. If the billing service has to go offline for an update, an asynchronous order service can just keep on accepting new orders. Those orders simply pile up safely at the post office and get delivered as soon as the billing service is back online. No data is lost, the business keeps running. That's the power of it. So, we've got the patterns, we've got the concept of time. The next logical question is, how do we actually implement all this? Well, let's look at the two main categories of tools we use to bring these ideas to life: invocation-based and message-based. This table lays out the fundamental choice, so let's just walk through it. With invocation-based tools, like a direct HTTP call, the data path is point-to-point. The sender has to know the receiver's exact network address. This creates what we call tight coupling. And here's the kicker: if the receiver is down, the whole communication fails. It's simple, yeah, but it's also brittle. Now, compare that to message-based tools. Here, everything goes through an intermediary, a message broker. This broker, our post office, will safely store the message if the receiver is down and just forward it along later. This gives us that amazing temporal decoupling. And it creates loose coupling. The sender and receiver don't even need to know the other exists. They only need to know how to talk to the broker. This right here is the foundation for building highly resilient, highly scalable systems. Wow, okay. We have covered a ton of ground here, right? We've gone from high-level strategy all the way down to specific patterns and tools. So let's take a breath and distill all of that down into 5 critical takeaways from our Architect's Handbook. Here it is, your cheat sheet. Number 1, in the world of microservices, communication isn't optional, it's mandatory. 2, asynchronous is the key to resilience. Using a message broker gives you that temporal decoupling to survive failures. 3, loose coupling is the ultimate strategic goal. It lets your teams build and deploy faster and more independently. 4, vocabulary matters. A shared language harmonizes teams and prevents costly mistakes. And finally, number 5, use the right tool for the job. HTTP is fantastic, but it's really best for those direct, synchronous requests that need an immediate answer. And you know what? That last point is the perfect setup for where we're headed next. Once you've got these patterns down, the next step is mastering the tools, and we'll be breaking down the 2 biggest players, HTTP and message brokers in our very next explainer. So we'll leave you with this one question to think about for your own architecture. Have you built a collection of elite specialists who just can't talk to each other? Or have you built a truly unified, resilient organism? Because to really master modern software, we have to stop designing just the components and start designing the conversations between them. That's where true resilience is really born.